Okay, we have been talking for the last couple of days about torques on current loops, and I tried to make the argument previously that this is an important topic. It's not just a side topic because it is relevant to things like electric motors and electric generators and subatomic particles and magnetic domains, magnetic moments of particles, etc. Things that you don't know a lot about necessarily. So I just want to spend a tiny bit more time on the torque on a current loop. So let's just say, again, I have this, as a review, this rectangular loop that I'm trying to draw in 3 dimensions now, and it's got current going around it, sort of. I mean, even though it's not necessarily supposed to be in the plane of the page, that current is going sort of in the counterclockwise direction. So the area of this loop, you take your right hand and you put your fingers in the direction of the current, and so the area points in the direction of your thumb, and so my area vector points sort of out of the page, right out of the page, circle with a dot in it. That's my area vector, and let's say that I put this in some constant magnetic field. It doesn't have to be a constant magnetic field necessarily, but we can calculate more easily for constant magnetic fields. And so we're going to get torque. The net torque on this loop is IA cross B. So the loop is going to tend to try to go to where the A vector is parallel to the B vector, because if the A vector is parallel to the B vector, right, this has in magnitude, the torque is IAB sine theta. And theta is the angle between the area vector and the B vector. So if theta is equal to 0, therefore A points along B. So we're going to have a tendency for the loop to line up so the field is going straight through its center, but in a particular, in the same direction as A, straight through its plane. Maybe I was a little unclear there. There is a torque on the loop equal to that, and that's going to make the loop rotate if the loop is allowed to rotate, and the loop will rotate until the torque is 0, right? So that's where theta is 0, then the torque equals 0. So the net torque on the loop is 0. I guess we can write this as the net torque on the net magnetic torque on the loop. So the torque on the loop is this one. At any angle, and if the loop is free to move, it's going to move until A is lined up with B. That's what I was trying to show here. So now I want to define a new quantity, and it's called magnetic moment. Magnetic moment is the Greek letter mu. It's a vector, and the magnetic moment is defined as I times A, right? So one of the things that we have a tendency to do, probably in all fields, but certainly in physics, is define one variable in terms of another, especially when it's a variable that we use a lot. Mu is called the magnetic moment. So it's the magnetic moment of the loop. So it's called the magnetic moment, in this case, of the current loop. So therefore, our torque equation is rewritten. Torque is equal, the net torque on the loop is the magnetic moment crossed with B. And that's a nice compact way. Now, the reason why we actually want to do this is because because we can generalize. And while we were talking about rectangular loops in order to calculate this, any loop at all, any shape, can be broken up into vertical and horizontal segments. And what I mean by vertical and horizontal, I mean like if our rectangular loop was in the plane of the page, we have vertical and horizontal segments, right? So if this was our rectangular loop, we've got vertical segments and horizontal segments. Any loop can be broken up, and we can find the force on each individual segment and add it up. And the effect is going to be that no matter what the shape of the loop, right? So even if it's a circular loop, you can break this up into infinitesimal segments that are vertical and horizontal, right? We can go around and break it up into infinitesimal segments and add up, right? The torque on each individual piece, which I guess we can just write as d torque. and you're going to find that the torque on each individual piece is the same torque. If we can calculate the magnetic moment of this circular loop, is the same torque as on a rectangular loop, because it can be broken up into horizontal and vertical pieces that are just like a rectangle. So therefore, the torque of this loop is also equal to the magnetic moment of this loop times the magnetic field, where the magnetic moment is the current in the loop multiplied by the area of the loop. So if there was a current going around the loop and an area, so therefore the area is pointing in a certain direction. In this case, again, out of the page, the magnetic moment of this loop is the current times the area, where in this case the area is the area of the circle. So this is actually not just for rectangular loops. This is a general equation. Okay, so I've been calling mu the magnetic moment. It is also known as more specifically as the magnetic dipole moment, because and I've said this before, that a single loop, like the loop shown in this page, creates a magnetic dipole. Remember what a magnetic dipole is. That a magnetic dipole, like a dipole magnet, a north and a south pole. This is the equivalent of that single little loop of current. So a little loop of current creates a magnetic field that looks like a dipole magnet. We'll talk more about that when we go to creating magnetic fields. But again, a single loop of current creates a magnetic field that looks like a dipole magnet. So this is actually called, as well as, I was calling it a magnetic moment. It's a magnetic dipole moment. One more thing I want to say about this, and that is, we've been talking about loops, but what about coils? So if you've got a coil of wire, that coil of wire is a lot of individual loops, right? Loop, 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 loop. I'm just pointing at the loops, loop. And each of those loops has an area A. So when we talk about the magnetic dipole moment, or the magnetic moment of a coil, mu of this coil, which is I times A, we got to be careful about what we mean by A. A is the total area by the loops. So we've got 1A here, 2A's here, 3A, oh, well, you know what I mean, sorry. We've got additional, so we got, if this is 1, 2, 3, 4, 5 loops, then the area is actually 5 times A, where A is the area of a single loop. So often the way this should be a vector. Often the way you see a magnetic dipole moment written is NIA, where A is the area of a single loop and N is the number of loops. So you just have to recognize that either if you write it like this, then A is the total area, sum of all the loops. If you write it like this, then it's the number of loops times the current in the coil times the area of a single loop. So this is basically, you could just write this. This is for a single loop, and this is for a coil. That's a way to look at it. Okay, now I'll do an example and then move on to the next chapter. Okay, so I've got an example of a solenoid, a loop of a coil of wire in a constant magnetic field. There's a lot of text here, but the text is just the words that describe the, I just need one more variable. It's the words that describe the different variables that define the situation. We can make it a lot shorter, and we will do so on the next page. But the solenoid is in constant magnetic fields. The magnetic field has a magnitude of 0.2 teslas. The axis of the solenoid is an angle of 30 degrees. Relative to the field, the area of a single loop of the solenoid is 10 to the minus 3 square meters. Solenoid has little n equals 3 loops per centimeter and is a length of 5 centimeters long. Current of 0.1 amps runs through the solenoid as shown. From the left to the right, or from the bottom to the top, depending on how you look at this. And so I got two questions. One is, what is the direction of the area vector? And two is, what is the torque on the solenoid? So let's first look at part A. So part A, what is the direction of the area vector? Well, the direction of the area vector is given by the right-hand rule, right? So the area is the area of a loop. And so if we look end on, right, so there's my eye. If I look end on, I see a loop that looks like this. And the current is going around that loop in a clockwise direction. And by the right-hand rule, if I put my fingers in the direction of the blue arrow, my thumb points into the page. Right, so my thumb points into the page, and so the area vector is into, from the way that eye is looking, the coil, and the area vector points in the direction of the green arrow. Along the axis of the coil from bottom to top, or from left to right. That's the direction of the area vector. Okay, so now let's write down the rest of the variables from the other page in order to answer part B. Okay, so I've written everything, all those words, as simply formulas or equations or whatever you want to call them, setting the various letters, constants to their numbers. And then we're going to use the fact that the net torque is equal to mu times cross B. And remembering that B is approximately in that direction. And notice that this is important, that the angle between the area and the magnetic field, that's the 30 degrees that was given. It wasn't necessarily, right? I gave you the angle between the axis and B. You can see for yourself that if A pointed in the other direction, the angle would be 150 degrees rather than 30 degrees. Okay, so we can just, now this is a pretty much just a plug-in. The magnitude of the torque is mu, which is IA times B times the sine of the angle between A and B. I is given. A is, whoops, didn't write that one down. A is given. This is where we need to be careful that A was the area of a single loop and we have multiple loops. So it's actually going to be the net area is N times A, where N is the number of loops. So let me just do an aside. The number of loops, total number of loops, is the number of loops per unit length times length. So the torque is equal to I times N times A, the area of a single loop, times B times the sine theta. Now these are all defined variables, and then it's just a plug-in for the magnitude of the torque. I've plugged in all the numbers, and these are MKS units, so in the end we are going to end up with MKS units. The one thing that I do want to point out for those of you who are a little weak on the units is that N is in loops per centimeter, and little n, the number of loops per length, unit length, and this length was in centimeters and really should remain in centimeters because that would then cancel with the centimeters on the bottom of loops per centimeter. Otherwise, we would have to change little n to loops per meter. So down here, I just did loops per centimeter times centimeters to give the number of loops in the coil, which is 15. In all those numbers, as long as I did it correctly. Not sure that I did, actually. Hold on. I lost a factor of 10 to the minus 3 originally. 1.5 to the 10 to the minus 4 Newton meters. And the direction, right? The direction is the cross product of A cross B, or mu, which points in the same direction as A. So you point your fingers in the direction of A, you cross them, you rotate them towards B, and that is into the page. Which also just means that the coil will rotate in the clockwise direction. The into the page is the same as the clockwise direction for this problem. Okay, there you go. Siri, tell me a joke.
They say you'll never go hungry at the beach because of the sand which is everywhere.
Huh, that was kind of funny. Okay, bye.